transversality is just neither nesting or being disjoint. Okay, so now there's some other structure that goes along with it, but for the rest of what I'm going to say, we don't need to say much more. So let me just remind you that there's a bunch of examples of this. So I'm going to abbreviate hierarchy hyperbolic spaces by HHS. So the motivating example is the mapping class group of S, where kind of the fact that these spaces are delta hyperbolic is this famous theorem of Mazur-Minsky, so the curve complex is hyperbolic, and sort of the study of the structure was kind of originally laid out by Mazur-Minsky, or with the structure that I've defined, so most of it was laid out by that. So mapping class groups, in general, right-angled arc groups, are also examples of hierarchy hyperbolic spaces. That was the example that Alessandro mostly spoke about the other day. In that case, the analog of the curve graph is something called the contact graph, which is a quasi-tree. And so maybe I'll say a little bit more about that later. So in general, at pi 1 of any special cube complex, and then there's more things. So under a slightly more general definition, you get relatively hyperbolic groups, and then you get three-manifold groups as long as they don't contain any nil or sol in their composition. So I'll just write three-manifold groups. And the list goes on, but those are the sort of basic examples. Okay. So the theorem, well, maybe I'll write the easy version of the theorem here, and then I'll write a more delicate version in a minute, because I set up a little bit of notation. So really the main theorem we proved is that the astim of a hierarchy hyperbolic space is always finite. So we prove finiteness, and actually we prove it with effective bounds, and I'm going to now tell you what the general setup is to get what the bounds are, and maybe try and sketch a little bit of the argument of why they're that.
So in the realm between hyperbolic functions and parabolic subgroups?
Have to be finite function. In general, they're hyperbolic with respect to any parabolic subgroup, but the finite asymptotic dimension statement only holds when they have finite asymptotic dimension.
Jason, you should put the word proper in this theorem.
Proper.
Proper HHS. That's finite asymptotic dimension.
Okay.
What about the definition of example? What about the examples of HHSs? Are you saying that all relatively hyperbolic groups are examples of HHS?
So I'm saying that all of them are examples of what's called a relative HHS. So these are relative HHSs. And for the asymptotic dimension statement, the asymptotic dimension of a relative HHS will work if the things are relative with respect to how finite asymptotic dimension. So step one. Okay, so I'm going to kind of go through. So I'm going to sketch the And actually, in the middle of the sketch, I'm going to give the more detailed statement of exactly what we proved. Okay, so step one is for any fixed hierarchy hyperbolic space, we proved that all the associated graphs, so all the associated hyperbolic graphs, C sub u, have a uniformly bounded asymptotic dimension. So we prove that in general, but in the case of the mapping class group, so our bound there is not the best possible in some cases. So for example, for the mapping class group, there's a better bound, so we don't have to really use step one because finite asymptotic dimension of curve graphs is already known. And in fact, for mapping class groups, the askim of C of S is equal to, what is it? It's 2 times the complexity of the surface plus 3. So this is by a theorem of Behrstock and Braun. Okay, so for mapping class group, we can skip this step. Okay, and I wrote that illegibly. So you can skip that step, and also I should say that for rags, you can also skip this step because I've already told you that the contact graph is a quasi-tree, so its asymptotic dimension is equal to 1. So for rags, the asymptotic of C of any of these C of U's is equal to 1. So there's already kind of explicit bounds in those two cases. So this step is not needed for those cases.
These lower bounds for the asymptotic dimension of the whole.
Actually, I should say, no, they don't give you lower bounds. Okay, so actually maybe I'll go to the middle. Okay, so let me now put up what the notation is, and we need a more precise statement. So, so here's a little piece of definition. So given U in script S, we say it has level 1 if it is nest minimal. Okay, so one of the parts of the definition which I didn't write down, but which Alessandro mentioned last time, is that under this nesting, there's a kind of finite depth to the complexity. So this kind of gives a measure. So this nesting gives a measurement of the complexity because there's only finite depth. So there's a unique maximal guy, and there's many different minimal guys, but there's always any chain has a minimal element, and there's sort of a finite depth between them. So the minimal ones I call level 1. And then level, in general, level K means that it's that the smallest, or the largest level of something that's nested inside it is level K minus 1. Okay, so etc. So in the case of surfaces, the level 1 ones are annuli; they don't have anything nested inside them. One level up from that will be 1 punctured tori and 4 hole spheres. Those will be level 2, and then level 3 will be higher complexity, and then it goes all the way up, and the top level will be just the full subsurface. Okay, the full surface. Okay, so that's what the level is, and then so we're going to let delta sub L equal to the max asymptotic dimension of any of the C of U, where the max is taken over of where U has level L. Okay, so if U has level 1, we're taking the maximal asymptotic dimension of the curved complex of an annulus. So we know what that is, and in general you kind of march up the levels. And then there's one other piece of notation I want here, which is that piece of L. The maximal number of pairwise orthogonal pairwise orthogonal subsurfaces of a given level. So that piece of L be the max is equal to the max cardinality of pairwise orthogonal level pairwise orthogonal elements of level L. Curve graphs of level L. Okay, so in the case of the mapping class group, piece of 1 is just how many disjoint annuli are there. Level 2 is how many disjoint, either 4 hole spheres or 1 punctured tori are there, and then it sort of marches up. So these give sort of two different numbers that we can associate to our given hierarchical hyperbolic structure. And now I can state the more precise version of the theorem. So the theorem that we prove is that if H is X is in hierarchical hyperbolic space, then the asymptotic dimension of x is equal to the sum. Okay, so the sum over these various levels, so the sum over L of the product of these two numbers, so P sub L times delta sub L. So you just take the product of these two things, and then you sum that over L.
So PL, is PL just axiomatically finite, or is this?
It's,
I mean, obviously, in all the examples.
yeah, so it's axiomatically finite. Yeah. Okay. So let's see. 5 more minutes, so let's see. All right, so
Is that, Jason, is that actually equality or is that just an upper bound?
sorry, did I write equality? Upper bound. Yeah, thanks. Good catch. Okay, so how do we do this? So the step, so that's what we want to prove. That's the goal. So step 2 is we introduce something that we call factor spaces. Factor spaces. Okay, so here's what a factored space is. I'm just going to sort of tell you in words. So you consider all the nest minimal elements, and then you collapse them out. Okay, so you collapse. So this is just collapse all nest minimal elements. So really, what you want to do is you want to collapse those distances, and so then you need to prove that you get a metric space. And you need to prove that it has the right properties, and that it's a hierarchy hyperbolic space. So then we prove this gives a new HHS, an HHS with lower complexity. Okay, and so it takes some work to prove that you get a hierarchy hyperbolic space by doing this. So essentially, right, so Alessandro mentioned the distance formula. You could, right, so the distance in the hierarchy hyperbolic space is made by summing over subsurfaces. So essentially what you're doing here is you're saying we're taking all the lowest complexity ones, like the annuli, and we're kind of ignoring all those distances. We're just coning those off, we get a new metric space, and then we need to verify the axioms for this new space to prove that we still have all the right structure. And you want to kind of do that, and you want to go up through the complexity levels. So this gives a new space, and then when we say that there's two properties of this, one is that you get so I'll call this x hat, and there's a Lipschitz map from x to x hat. Okay, and so in general, since I'm 1 minute away from overtime, I think, and Henry's nodding his head, so you get this Lipschitz map, and then we prove. So step 3.
He's drawing a couple minutes late.
Oh, did I? Okay, well then I'll take another 15 minutes. Okay. No, but maybe I'll write out the 2 steps then instead of kind of just glossing over them. So what do we do? So the next thing we want to do then is that we want a way to invoke what's called a fibering theorem in dimension theory, in which there's a version of an asymptotic dimension due to Dinish-Coff and Bell. So you have a Lipschitz map from one space to another space, and it turns out that if you can bound the asymptotic dimension of point inverses of this map, then you get a bound on the asymptotic dimension of the original space in terms of the asymptotic dimension of the target space and the asymptotic dimension of that point inverse. So it'll be the sum of those two things. So if you have a space here, which is now lower complexity, and if we can understand the point inverses is bound the asymptotic dimension of them, point inverses of small balls, or of balls at a given radius, then you get a bound on the dimension here in terms of the sum of the dimension of this and the dimension of those point inverses. So we prove in step 3 that for every r and for every point in this space, the asymptotic dimension, let me give this a name, I'll call this phi, okay, then the asymptotic dimension of phi inverse of the ball around X of radius R is less than or equal to the astim of some set X, O, which is, so this is the this is a maximally pairwise, so it's a maximal set of pairwise orthogonal subsurfaces. Okay, so that gives me, so Alessandro mentioned last time that these kind of these products, these give you things that are like products inside the higher hyperbolic space. And so I take sort of a maximal product, and I look at the asymptotic dimension of that, and that gives me a bound, an upper bound on the asymptotic dimension of point inverses. And so therefore, so hence the dimension of the asymptotic dimension of X is less than or equal to this astim of what it is for O plus the asymptotic dimension of X hat. Okay, and so now the sort of the magical thing is that we've left the world of mapping class groups because now we've done this weird quotienting. So we're no longer in the world of mapping class group, but now we have a new hierarchy hyperbolic space, and so we can just repeat this argument again. And so now we've got this kind of this new space where we've combed off a bunch of things, and we have, it's still a hierarchy hyperbolic space, so we can now look at the nest minimal ones there, and we can keep going. Okay, so step 4 is to induct. And so you get this map, you get a Lipschitz map from X to X hat, and then you get another one that goes to X hat hat, and then to X hat hat hat, and we have better notation in our paper, but it just kind of keeps going, and it stops, and finally in many steps, at the very end, you reach C of S. So the last one here is C of S, and we know that has asymptotic dimension, and then you sort of work your way backwards. And so maybe I should stop now.
Any other questions, Jason?
So yeah, O is it's written here legibly small. It's a maximal set of pairwise orthogonal subsurfaces. So I look at the, I should have said nest minimal. So you look at sort of a nest minimal collection of subsurfaces which are pairwise disjoint. So in the case, like in the first level of the mapping class group, what you do is you just look at annuli and you look at sort of the Dane twist flat generated by those annuli. And that dimension is the dimension you get here. And when you go one level up, it'll be a collection of sort of pairwise disjoint one punctured tori, a maximal collection of those. You take the product of those. So either they're all disjoint, and so you kind of take each one of those separately, and you have this gives you a subset inside the original space.
So what is O? It's a space.
Right. O is a right. It's a subspace of X, which is given by the product of these independent of spaces that are associated to sort of these independent pairwise orthogonal things. So in the mapping class group case, at the lowest level, it's the Dane twist flat. So yeah, it's flat product. It's sorry, product. Yeah, it's the product of this set of maximal pairwise orthogonal things that are just in here.
Thank you. So we'll start. Let's take a 5-minute break and then start again. First, let's thank Jason.